As we know, in a single phase half-wave voltage controller, the output voltage and input current are asymmetrical and contains a DC component. This problem of DC input current can be prevented by using bidirectional control, which is nothing but full wave control. So, single phase full wave voltage controller or bidirectional voltage controller with resistive load. This is our input waveform. In positive half cycle, T1 is triggered with the pulse at alpha, then the input is going to reflect in the output voltage, and in negative half cycle T2 is triggered at an angle pi plus alpha, so that the firing angles of T1 and T2 are kept at 180 degrees apart. Then the input voltage is going to reflect at the output. In the next positive half cycle, T1 is triggered. So when T1 is fired at alpha 1, the current flow is Vs plus to T1 to load to Vs minus. When T2 is triggered at pi plus alpha 1, the current path is Vs minus or to T2 to Vs positive. You can see at R, in positive half cycle the current is coming from top to bottom, whereas in negative half cycle the current is flowing in the reverse direction. That is why we are going to get a positive output as well as negative output in AC voltage controller, whereas in rectifier circuits both will come in the positive only, since the current direction is not going to change. The angle between these two firing times is 180 degrees or pi. If Vs is the input given by root 2 Vs sine omega t, the angles of the thyristor T1 and T2 are, for T1 it is alpha 1, for T2 it is alpha 2, which is nothing but pi plus alpha 1. Alpha 1 equals to alpha 2 equals to just alpha, since the angles are equal. Now the RMS input voltage V0 is given by 2 by 2 pi integral alpha 2 pi 2 Vs square sine square omega t d omega t, everything comes under the square root. 4 by 2 pi Vs square integral alpha 2 pi 1 minus cos 2 omega t by 2 d omega t, everything under the square root. Then if you solve this, we'll be getting Vs square by pi. So 1, if you integrate omega t, you are going to get that pi minus alpha plus sine 2 alpha by 2 whole thing under the square root. V RMS or V0 equals to Vs of 1 by pi of pi minus alpha plus sine 2 alpha by 2 under the square root. So by varying alpha from 0 to pi, we can vary VRMS. If alpha equal to 0, this will be 0, so pi by pi gets cancelled, and this is 0, then sine 0 is 0, so this is also 0. Then we will be getting Vs. If alpha equal to pi, pi minus pi is 0, this is also 0, then VRMS will be 0. Now, in this circuit, the gating circuit for thyristor T1 and T2 must be isolated. It is possible to have a common cathode for T1 and T2 by adding two diodes as shown in this circuit. Here, in positive half cycle, the power is going to flow through T1 and D1 to the load back to supply. In negative half cycle, the power is going to flow through load to T2 to D2 to the supply. So you can write this Vs positive, T1, D1 or back to Vs negative in positive half cycle. In negative half cycle, Vs negative or T2 and D2 to Vs positive. Since this circuit can have a common terminal for gating signals of T1 and T2. Here we need one isolation circuit, but at the expense of two power diodes. You can also, here two power devices are acting at a time, and here also two power devices are acting at a time. Due to this, the conduction losses of device would increase and efficiency would be reduced. This is a single phase full wave controller with common cathode circuit. Now, a single phase full wave voltage controller can also be implemented with one thyristor as shown in the circuit with 4 diodes. The four diodes acts as bridge rectifier. The voltage across the thyristor T1 and its currents are always unidirectional with the resistive load. The thyristor current would fall to zero due to the natural commutation in every half cycle. However, if there is a large inductance in the circuit, thyristor T1 may not be turned off in every half cycle of the input voltage, and this may result in loss of control. It would require detecting the zero crossing of the load current in order to guarantee turn off of the conducting thyristor before firing the next one. The bridge rectifier and thyristor acts as bidirectional switch, which is commonly available as a single device with relatively low on-state conduction losses. You can observe in the circuit, in positive half cycle, T1 is triggered at an angle alpha with gate pulse. Then input is going to appear across the output. Then the conduction will start flowing from Vs positive to D1 to T1 through this D2 to the load back to Vs minus. Then this is our output waveform in the positive half cycle. In the negative half cycle, again thyristor need to be turned on at pi plus alpha 1, which is equals to alpha 2 in our case. Then when this thyristor is again turned on, then the supply voltage will be from Vs minus to R to D3 to T1 to D4 to Vs plus. Here also 3 power devices will be in operation at the same time. Obviously the efficiency will be reduced as well as conduction losses of the device will increase.